talk about bifurcations. Okay, so we're going to talk about typical bifurcations of equilibria. Okay, let's write that. Of ODE systems with one parameter. Right? So this is in relation with what we did in the last lectures. We showed persistence of some equilibria, right? Like they survive the process of jiggling a parameter. Well, these ones, will be, when we jiggle the parameters, something might happen. It's either they disappear or they're more, or something happens, right? In any case, the theorems the theorem that was assuring that the equilibria persist is not applicable, right? So we'll have a condition there that will not be there. The typical bifurcations of equilibria of nonlinear ODEs, okay, systems, ODE systems with one parameter, okay, because if we have more, it's basically more and more complicated and hard to say something in general, okay. And also, when you have 2 or 3 parameters, you just get into PhD subject theses, even like big time, you just have to be patient, and sometimes it's very hard to visualize anything. Okay, so here is the object of interest. So we have an ODE system that looks something like this. Okay, so X belongs to a domain somewhere in Rn, okay, and epsilon is one-dimensional, is in R, right? So we already, okay, so let's assume, okay, that when epsilon is 0, right? Okay, so I don't need to put a dot. Okay, assume that when epsilon is 0, we have an equilibrium. Okay, so some x naught, an equilibrium. In other words, f in 0 and x naught is 0, right? Because equilibria are found by making the right-hand side to be 0. Now, we know that if we do the partial of f of this right-hand side with respect to x at that particular point, right, at 0 x naught, if this partial has the determinant non-zero, right, because I put it in Rn, if determinant of this guy is non-zero, then the equilibrium will persist for small values of epsilon, okay? Then the equilibrium persists for small values of epsilon, i.e., okay, for any epsilon small, right, small like near 0, okay, in some vicinity of 0, in some neighborhood of 0, there is an x which depends on epsilon, okay, such that f in epsilon and this x of epsilon will be 0. So if you recall, we denoted this x of epsilon as g of epsilon in our theoretical part, but essentially that's what it is. X, is still there at the root, it's just, it will depend on epsilon, it's still there. So now, what about if this wonderful condition, this one, is not there anymore? We cannot say that the equilibrium persists because the condition is not there. So what do we do, right? So that's exactly what we're going to talk about today. So if determinant of df dx in 0 x naught is 0, then what do we do? Then we are in big trouble. Okay. Okay. So what I'm going to do, I'm going to turn the page and see how we can get out of this big trouble. So essentially, you know, we do this discussion in terms of the derivative of the right hand side there, you know, at the equilibrium point, or at, you know, this epsilon and x, right, by expanding the right hand side in a Taylor series, right? That's how we did the linearization, right? So we say, oh, near an equilibrium, you know, we're going to expand the f, and because it's, you know, and get rid of the higher order terms and just keep the linear approximation, right? That this is the philosophy, right? And the linear approximation will tell us, you know, that's a linear system, how the dynamics is, you know, near the equilibrium, because things are, you know, kind of the same, right? You know, curved space, localized there, just right there around, is almost a flat space. So things are kind of fitting, okay. But in this case, you know, it doesn't work like this, because, you know, we cannot say that, you know, locally it looks linear, because the linear term kind of dies, right? So what do? You go to the next term in the Taylor expansion. So basically what one has to do, okay, so we're gonna go to expand the right hand side, right, the f, okay, in Taylor series, around 0 and x naught, and consider higher order terms. Okay, so I'm going to write that expansion just once, you know, and kind of look at it, because I don't really want to get into the theory of how to do this for each type of bifurcation, because that's what will emerge. But I just want to kind of show you the philosophy, what one does, you know, in a calculation of some of this sort, okay? And actually this kind of stuff is what they do in a master's, let's say, you know, a master's project would be just perfect kind of understanding how this, the bifurcations I'm going to talk about, you know, are obtained. So basically this is written as, you know, so the base point is this one. So near this guy, f of epsilon and x looks like what? F in 0 and x naught plus df d epsilon at 0 and x naught times epsilon minus epsilon 0, but is 0, plus df dx at 0 and x naught. This df dx you can think of it as x being in R or x being in Rn. If it's in Rn, is the Jacobian, right? So, all right, and then x minus x naught plus a half, and now comes, you know, terms of order 2. So it will be d2f, d epsilon 2 at 0 and x naught plus, times epsilon squared, plus, now we're going to have two terms that kind of look the same. And because I consider the Rn case, I have to write it something like this, x minus x naught transpose. So this is a vector, but it's transposed. And then this second derivative, okay, however it's calculated, and then x minus x naught. So this is the term of order 2, okay, but it's just one. And now comes the double term. So this is in 2 d2f d epsilon dx epsilon times x minus x naught, and then plus, it keeps going, right? Higher order terms. Okay. So why are two of these? Because actually this guy, it's one is this way and the other one is the other way. But we assume that the function f is nice enough in other words, if f actually, this is valid, is f is of class C2, okay? So class C2 would mean that is twice differentiable with the derivative of order 2 continuous. So in that case, you know, these guys can, right? I can switch the order of derivation, okay? So we assume that anyhow, we assume that our f is so nice that we can take derivatives of any order actually, right? So we don't really go into, you know, technicalities. We just go with the, you know, with the big machine now. Blah. All right, so what happens in this special case? Okay, so this is 0 because of the equilibrium. This is 0 because we're in that case where is no persistence, right? We don't know about persistence, right? So I can put persistence, we don't know persistence. The point is that the implicit function theorem doesn't function anymore. So we end up with this term and then whatever is in this bracket, right? And we can, what people do from here on, okay, they say, look, I'm gonna truncate the expression here, and I'm gonna look at zeros of this right-hand side. So, you know, I'm gonna try to solve df, the epsilon, okay, plus 1/2, whatever it is there, okay, blah, 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 equals 0. You know, so I'm going to try to solve it for x as a function of epsilon, okay? So solve for, you know, so whatever the expression is there, in here, it would be something like a quadratic because the terms x show up as an x squared, right? These guys are just entries with numbers, right? It's like a matrix with numbers and stuff. So the philosophy is that I'm going to go to the higher order terms in the Taylor expansion, and I'm going to still try to solve the equation somehow, okay? So for, you know, it's if I can. And it turns out that then, you know, once we solve this one that is truncated, we apply again an implicit function theorem argument to argue that that root that we found at order 2 actually survives when we take the higher order terms in consideration as well. Yeah, smart, huh? So it's again based on the implicit function theorem, but is a little bit more, you know, delicate, more, you know, the calculation is more involved. You know, we really have to know what we're doing. It's not just 3 and 5 as numbers, right? But the philosophy is the same. Look, I'm going to take higher order terms. I'm going to truncate wherever, you know, I can, that it makes sense, try to solve it, get an x of epsilon, and then show that that actually survives, you know, if I put the higher order terms in the expansion as well, okay? So people did this a good while ago, I think. Actually, I don't know who did this first time. Okay. That's a good question. But the textbooks that, you know, I studied from, you know, they are basically about 40 years old, okay? And I think in the 70s, in last century, it was like an explosion in applying results in nonlinear dynamics to real life systems and, you know, whatever, even climate dynamics or something like that, okay? So bottom line, what follows now is that, you know, we're going to assume that someone did this job for us, and we're going to write down what are the typical bifurcations when we have one parameter in the problem. So the parameter being epsilon is one dimensional, okay? And somehow people reorganized the dynamics that basically reduced it to a one ODE with one unknown. So we're going to talk about typical bifurcations in this case, okay? So you're going to say, oh, you know, it's basically you're going to study just this. And I can tell you, well, it's not just this, because many of the, so this is the domain is in R, many of the problems that are higher dimensional, right? And have a parameter, actually you can manipulate, you can change the variables, you can change the reference frame, however you want to think about it, and you end up to the essential bit, which is a one ODE with one parameter in R. Okay, so that kind of manipulations is called bringing the system to a normal form. Okay, and that's another one of the subjects that would be studied in a higher level dynamical systems course. Okay, so this being said, I can show you some typical bifurcations. Okay, so I'm going to put it here, typical or generic, you know, the right word is generic bifurcations. Okay, so before I start, I just want to make a bracket about the word, the use of the word generic. If we take, so I'm going to give you an example. Okay, so if I'm talking about the position of a line in the plane, generically, a position of the line in the plane would cut one of the axes. Okay, so generically, if I take a line in the plane, it will cut OX. Okay, a non-generic case would be when this line is parallel to the thing. So whatever is like really unlikely to happen is non-generic, whereas whatever is very likely to happen is generic. For instance, if we take a matrix, another example, here is another example. If you take a matrix that is n by n, so any n by n matrix, let's call it A, okay, generically has its determinant non-zero. Okay. Well, it's so rare to have the determinant of a matrix to be zero. This is rare. And there is a theory in topology that, you know, actually defines this word generic properly. Okay. But I'm not getting into it, but that's the use of the word generic here. Okay. So here, one, the saddle node, saddle node, okay, bifurcation, okay. So this refers to the equations 1D that after we do, or, you know, systems of equations in higher dimensions that are reducible to the normal form that looks like this, okay. So their essential part, after we cut the higher order terms are cut, we don't see them, okay? The essential part is this one, what you see here, okay? So now we're going to discuss the roots of this equation, okay? So the roots, the equilibrium, right? So we have, right? So we do, yeah, I'm going to write here equilibrium, right? So we have epsilon minus x squared is 0. So we end up with what, right? With x squared is epsilon. And now I'm going to say if epsilon is negative, there is no equilibrium. Whereas if epsilon is positive, we have x1, 2 plus minus root epsilon, okay? And epsilon equals 0 is the bifurcation bifurcation point, if you want, okay, okay, in the parameter or on the parameter axis, okay. So usually I say in the parameter space, but this is, the parameter space is just one dimensional, on the parameter, which is the epsilon axis, okay. So how do we represent this? It's the so-called bifurcation diagram, which looks like this. We take the horizontal to be the parameter axis, that's the epsilon, and the vertical to be the number of equilibria, the equilibria, represent the equilibria there, okay? So here, this is the epsilon, and this is the equilibria if you want, okay? So now, for epsilon non-zero, we have no equilibrium, so I'm not drawing anything. Whereas for epsilon positive, I have two branches, right? So I have a branch up and the branch down, okay? So this is x is root of epsilon, and this is x is minus root of epsilon, okay? All right, so what about the stability of this stuff, right? So what about the stability of this equilibrium, right? So what we have to do for stability, okay, you don't have to do anything. I'll just shift the picture so I have everything on one page, okay, guys? I always have a problem with the space on this tablet. That is why I don't like writing on the tablet, but at the board, right? Because there I can get organized as I want. Okay, here. Good. Epsilon. Okay, equilibria. Okay, and what did I do? I did these branches here. So now I needed room for the stability. Okay, so for the stability, we have to do the linearization, right? So it's given basically by the derivative at the equilibrium of the right-hand side. So in this case would be f prime computed in an equilibrium, right? That's what we have to do, right? So we have to do f prime, which is minus 2x, and then to put x to be an equilibrium, right? So on purpose, I'm not putting the thing in yet. Right? So for x1 is root epsilon, then f prime in x1 would be minus 2 root epsilon, so it's negative. So this x1 will be stable. Yeah. Whereas for x2, which is minus root epsilon, we calculate the derivative at x2, which is 2 root epsilon, which is positive. So there you go. It will be x2 is unstable. Okay, so it's repelling is the real part, right, as we discussed. But this is like for 1D, not 2D. So you don't have lambda 1 and lambda 2. You have just lambda, just 1, right? Because this is like a matrix with that is 1 by 1. Okay. So now to represent the stability in the diagram, what I'm going to do, I'm going to leave the unstable part to be dashed, and the stable part, I'm going to fill it in. So there you go. So that's stable, whereas this guy is unstable. So as epsilon shifts, you know, in 0, so up to 0, there is no equilibrium. And from 0 on, we have two branches of equilibria, two possibilities of equilibria. One is stable and one is unstable. And this guy here is called the bifurcation diagram. Bifurcation diagram. Okay. Yeah. I think it's quite straightforward. Okay. So I'm ready to move on to the next typical bifurcation. Okay. Which is the transcritical. So 2. Okay, we have the so-called transcritical bifurcation. Okay, I don't have to write that. Okay, transcritical case. So in this case, the normal form of the equation, so this simplified essential equation that catches the bifurcation is this one. And again, we're going to do equilibria. Okay, so we end up with x times x um, minus epsilon is 0. So we're going to have x1 is 0 is an equilibrium for sure. And then x2 is the other equilibrium. And then I'm going to draw the picture. Okay. All right. So this is the epsilon. This is the Equilibria axis. So we have x is 0 for all epsilons, and then we have x is epsilon for, again, for all epsilons. So there is no, there are two branches for every epsilon. So for every epsilon fixed, we have two equilibria. One is 0 and one is the other one, right? That's what it means, this graph. Okay. So now what is the stability of this equilibria, right? Stability, okay? So for this one, we're gonna do f prime of x, which is epsilon minus 2x. And we're gonna introduce in there the equilibrium. So f prime in x1 is f prime in 0, which is epsilon is positive. So f prime in x1 will be positive for epsilon positive. Oh, sorry. So it's epsilon, right? Okay. And will be negative for epsilon negative. Yeah. In other words, f prime in x1, so, or actually the conclusion of this is that then x1, which is 0, will be stable. No, first is unstable because it's positive, right? So unstable for epsilon positive and stable for epsilon negative. I told you that this is not hard stuff. So I'm going to draw it as such. So unstable for epsilon positive will just stays dash, whereas stable for epsilon negative, so I'm going to fill it in. So this is stable, okay, whereas this is unstable. And now I have to do the same thing for the other equilibrium. So if I do f prime in x2 is f prime in epsilon. So this is epsilon minus 2 epsilon, so it's minus epsilon. So it's exactly backwards like the other one, right? So dot, dot, dot. So we're going to end up that x2, which is epsilon, will be stable for epsilon negative and unstable for epsilon positive. Huh? What it was stable for? No. It's exactly backwards. Stable for epsilon positive and unstable for epsilon negative. Okay, so the picture is stable for, so this is the branch that goes diagonal. Right? So there we go. So this is stable, right? So this is x is epsilon. And this is x is epsilon again, and this is the unstable part. I'm just writing for you stable, unstable, but once we get this convention that whatever is fully stable and the dash line is represents unstable equilibria, then it's done. Okay, so there's the second one. So you have some exercises asking you to recognize this. And then we have the third one, which I like most. I like most because it shows up in the systems that I study, right? The Hamiltonian systems. Okay, so this is called the Pitchfork. Pitchfork bifurcation, okay? And the Pitchfork shows up in systems for which the so-called normal form is like this. Okay, so again, we're going to look for equilibria. So we end up with x times x squared plus epsilon is 0. So we're going to have the following, right? We're going to have x1 to be 0. This is an equilibrium for all epsilon. And then we end up with x squared is minus epsilon, right? So basically, we have x1 is 0, is an equilibrium for all epsilon. And then for the others, we're going to have x2, 3 is plus minus root of minus epsilon if epsilon is negative, and nothing else if epsilon is positive. So the diagram will look something like this. So here is epsilon, right? So we have a 0 for all epsilons. And then we have these branches if epsilon is negative. So I better put them here. Okay. So this is x is minus root of, no, minus, plus root of minus epsilon. And this is x is minus root of minus epsilon. That's how the picture looks. I don't need this line so long, so I'm going to shorten it. Oops. Yeah, so it's like a pitchfork. That's why it's called the pitchfork. Okay, so now we have to see the stability. Stability. Okay, so let's do f prime of x is epsilon plus 3x squared. And now we're going to plug in the equilibrium. So we have for x1 is 0. Okay, we have f prime in 0 is epsilon. So we're going to have that x1 is stable if epsilon is negative, because that will be minus, right? And x1 will be unstable if epsilon is positive, right? Because, you know, if this is negative, f prime in 0 is negative, linearization is like the real part of the eigenvalue is negative. So in this case, it's just one eigenvalue and it has just real part and is negative. So it's stable, done. Okay. And so let's draw it. Okay, so it's stable here. Okay. And now for x2, which is plus minus root of minus epsilon, if we do f prime in x2, this is epsilon plus 3 times minus epsilon, right? Because x squared, okay, would be this guy squared, which is minus epsilon, just to make sure your algebra is there. Yeah? Okay. So this is minus 2 epsilon. So it's negative. Okay. Right. All right. So now we end up with f prime in x2 will be, so this would be stable. Oh, but these guys exist only for epsilon negative, right? Okay, so I don't have to look on cases. This is directly, so this will be positive since epsilon is negative. So this means that f prime in x2 will always be positive. So this means that x2 will be unstable. So it stays dash. Right? As a note, okay, so I always forget which one is subcritical, supercritical. There are more pitchfork cases, okay? So essentially they're like this one, but you know, you can have the pitchfork to be stable, like this. And then this thing, it's a switch here, right? So there you go. That's another case. So the 0 is backwards with respect to what we draw, right? So it will have the branches to be stable and the 0 to be unstable and then switching to stable. Then another one could be reversed with respect to the direction. So you could have something like, and then, okay, so if you Google Pitchfork bifurcation, you'll see all these cases there, and the denominations. I never remember which one is subcritical or whatever, but I do remember the fact that there's always a switch on the 0, 1, and the branches are the same. Okay, so all these are pitchforks. So these pictures appear as we change the signs here. So if I would put a minus there, you know, the discussion will be a kind of the same, but it leads to a different picture down. Okay, if I put a minus here, or if I put a minus here and the minus there, that kind of stuff. So I'm not going into, I think I put in the homework some of this. Okay. Homework, the recommended problems. Okay. So there's that. So this is the easy part, isn't it? So these three bifurcations are the generic cases that, or the typical cases that appear in systems with parameter. There is one more with respect to periodic orbits, so that's a little bit different. And there is no other possibility. That's what I'm trying to tell you. So somehow, all bifurcations, at least for 1D systems, or for the systems that reduce their essential normal form to a 1D ODE, okay, they're all reducible, or they all can be transformed to one of this, okay? So it's either one of this, or one of this, or this one. There is no other possibility. That's why they're taught. That's why people are telling you about them. Okay? That's why I'm putting them in the course. All right. There is no other possibility. So there is a theory that shows that there are no others, and you know all of them are coming into this one of these three buckets. Okay. So there you go. Now for the fourth one, which is called, and is the most, not the most famous, but people really love it, is the Hopf bifurcation. Okay, and it doesn't refer to Equilibria, but to periodic solutions. So we have to do a little bit of a side note with respect to what is a periodic solution, what is a limit cycle, and that kind of stuff. So where is it? Where is it? There we go. So as a philosophy, right, this one, it concerns the birth or death of periodic orbits when the parameter is varied. It concerns the birth, death, change in stability, okay, whatever, of periodic solutions as a parameter, or as the parameter, because we're having one, varies. Okay, so to start, we have to define what is a periodic solution. So here, let's take an ODE. Okay, X is in D, in R, and doesn't really matter. Okay, so definition. A solution of, let's call it star. Okay, so let's call the solution X of T. A solution X of T of star is periodic. What do you think it is? It's a periodic function in T. Right? Okay. If there is a T positive such that x of t plus t is x of t. T is the period, okay, and is chosen to be the lowest positive number for which x of t is a periodic function, right? So it's the minimal t, okay? So I won't get into, writing. It's the smallest t. So for instance, sine of x, right, or sine of t is 2 pi periodic, although, you can think that is also 4 pi periodic or 6 pi periodic, but t is the minimal period, right? So it's the lowest positive number that does the job. And not t is 4 pi, or I don't know what multiple of 2 pi. Okay, so that's what is a periodic. Okay. All right. Now, another definition is, what does it mean that the periodic solution of an ODE is isolated? Okay, so I'm going to make first a picture. Okay, so let's say we have, here is t, and we have a periodic solution, could be sine of t. Okay, doesn't really matter here. So it keeps going. Okay, so what, and it going in the back too. So what will mean that this, let's say this is a periodic solution, okay? What would mean that is isolated, it means exactly what it sounds. If I take some neighborhood of it, which in this case would be like a band that surrounds it, I will not find any other periodic solution around it, okay? So whatever other solutions that are around will just be non-periodic. I'm not saying that they go to infinity or they diverge, it's just they are not periodic, that's all. So if I take here a band around it, okay, so here is like a tube if you want, okay, so here is a neighborhood, and then in this neighborhood, okay, I take any other solution, that one will not be periodic. So it's somehow, maybe it stops here, okay, and then it starts again, I don't know, okay. So the point is that this one, maybe at some point will just not be periodic, okay. It doesn't come to the same place, so I don't know how to make it that it doesn't, it's almost periodic, but it's not, okay. So the blue one, not periodic. This is, I have difficulties because I'm drawing in 2D. If it would be in 3D, it's simpler because they can go, blah, 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 right? They're curves, right? So they can. Okay. All right. So let's write the definition, right? So periodic solution. Okay, I have to change my color. Okay. Periodic solution is isolated if there is a neighborhood of it in which we cannot find any other periodic solution. Okay, so if I start near, I'll have a solution, but it's not periodic. Okay, it's just that one. It's very special. Okay, so as a denomination, an isolated periodic solution is also called the limit cycle. Okay, is also called a limit cycle. Okay. All right. So big questions. Can I have an example of an isolated one? And do I have an example of non-isolated ones? Yes, I do have both. Okay, so there you go. Let's see. So that's where, you know, it starts coming, you know, the polar coordinates start to be kind of relevant, because R would be constant, something like that. Okay, so here is an example. Okay, so we have in polar coordinates the following system. Okay, and theta dot is 3 theta. So it's a system in R and theta. It is separable, right? It's uncoupled, but it's still in R and theta. So when I'm going to do a drawing, the face plane has R and theta, has X and Y, and then, you know, polar coordinates R and theta. So here it is, right? So I have to do an X and Y coordinate. Okay. All right, so that would be the X and then the Y, and then I'll do the drawing in R and theta. So this one, you know, it's easy because when we solve, for instance, the theta equation, this one pops out instantly to be E at 3t times theta naught. Okay, so that's solving it, blah, blah, blah. It's like the first separable ODE that one can, that you're taught in calculus 1, for instance, at the end. Whereas for the first equation, right, I'm not trying to solve it. What I'm trying to detect if there are solutions for which R would stay constant, okay? So because for those ones, you know, R will stay constant will be like a circle, right? So it's a circle and theta evolves after that E at 3t, right? So it'll be like whatever, right? As t goes, it's probably that's going faster. But, you know, it will stay on a circle. So if we do, so I'm going to write here this equation. And I'm going to do the right-hand side equals 0. So in other words, this stuff is 0. So we get that R1 is 1 and R2 is 2. Believe me. Okay, so I chose the numbers in this way. We will have that this R1 of t is 1 and theta of t is E at 3t, some theta naught. This will be a periodic orbit. Okay, I'm going to write periodic orbits like this, PO. Okay, and actually I can draw it, right? I can make here a periodic orbit of radius 1. Oh, what was that? Okay, now comes the pain. Huh? Come on. I'm trying to center it. Probably I won't be able to. Okay. Something. Okay. So this is for R equals 1. Okay. Whereas we do the other one. So for the other one, we'll have R2 of t is 2. And theta of t is again E at 3 theta, theta naught. So this is another periodic orbit. Okay. So if I draw it, okay. So let's see. Something. Okay. So this would be 2. Radius 2. Okay. So these are two periodic orbits. They're there, right? And actually, we can even say in which way the arrow goes. Okay. So theta is increasing, isn't it? Yeah. So as t is going, so as t goes up, right? If t increasing, you know, you have actually don't even, you know, so. Right, so as t is going up, theta of t, let's say that theta naught is positive, right? So I would think that is going this way, no? Because theta is increasing. Good. Okay. So I'm just thinking about something silly. All right. What else can we say about these periodic orbits? Oh, we can say, you know, that they're kind of isolated, because if they're not isolated, if I'm looking, so this R equation, so this is R minus 1 and R minus 2, right? So we'll have that, for instance, R dot is positive if R is outside the roots, right? So maybe I should write somewhere there. So R dot is positive, i.e. R would be increasing if R is in between what? So R is positive anyhow, because this is polar coordinates. So we'll be in between 0, no, so it's out the root. So it's from 2 to infinity, whereas R dot will be negative, right? So R would be decreasing if R is in between, so what am I doing here? Right, outside the roots. So this should be 0, 1, union to infinity, whereas this was in between 1 and 2, in between the roots, yeah? So R won't stay fixed. That's the point. If I start somewhere in between, I have to, I don't know exactly where I'll go, but well, I actually can say where I'll go, because if it's in between 1 and 2, R is positive, so R will increase, right? So I can actually do a drawing. So here I start here, and then R will decrease, right? So it's going towards this guy in, right? So I can say it's something like this. Okay. Okay. So backwards in time, if you want, is coming from the other circle. So it comes asymptotically from the outer circle, and it goes asymptotically towards the inner circle, if you want. Yeah. Whereas for the other side, when it's in between 0 and 1, R is increasing. So if I take here a thing, right? So it's increasing, so it's getting larger and larger. So it's going asymptotically towards the green circle again. I should do these guys thicker. So these are the objects of interest, these green circles. All right. Whereas if I'm, again, from 2 on, so I start somewhere here, what happens, right? Again, I am increasing with R, so I'm going to go outwards. Yeah, okay, whatever. Yeah, got the idea? Yeah, that's okay. Do we really have to do this analysis like this? Yes and no. We could do it in a different way, and the way I like to do it is really to look at the R equation and do the linearization for that one. In different words, what I'm saying is that we could do like a reduction. Look, to understand what's going on in this picture, in between the green circles, is sufficient to look at the dynamics in the R direction. Okay, so it's like it's a quotient space. So all guys with the same R, right, with the same distance from the origin, they will be considered actually 1 point, right? So the entire circle is reduced to 1 point, right? You don't do any topology, but that's exactly what topology does to us, okay? So it allows us to reduce objects that are really have something in common big time, like, the radius is the same, right? So all these points on this circle of radius 1, I can put them, shrink them to 1 point at distance 1 from the origin if you want to think like this, right? Okay. So here is sufficient to look just at the R equation and to do the stability for it. So this is the right-hand side here is f of r, right? So this f of r is r squared minus 3r plus 2, yeah? And then I'm doing f prime of r, the linearization, which is 2r minus 3. And now I'm doing f1 in 1 will be minus 1 is negative. So this means that r1 equals 1 is stable. So because it's stable, it attracts, okay? It attracts the um, orbits around, if you want. Okay. So that's another way to do it. And then I could do f prime in 2 and see what I get there, right? So when I say it attracts, you can see what's happened, you know? So if we start here inside, right, you know, it attracts, it goes towards them, you know? If I start out, you know, again, it goes asymptotically, it tends to it. So this circle of radius 1, you know, all the orbits around are coming, wrap around, you know, asymptotically to this particular circle. Whereas the other one, if I would compute now f prime in 2 probably will be positive. I mean, I know it's positive, right? It will be 4 minus 3 is 1, right? So it's unstable, so it repels. So this radius 2 circle, right, orbits around it will go away, right? So if I start near r equals 2, I'll go away. If I'm outwards or if I'm inwards, I'll go away wherever I can, right? So I'll go inside the other one. So this is like the stability analysis of a system in polar coordinates, okay? So now, obviously, this R1 and R2 are isolated, right? Because any orbits around them, right, are not periodic. So for r equals 1, yeah, I can find the neighborhood of it, obviously, that, you know, I can take the neighborhood as not as big as I want, but big enough, you know, is large enough to see that no orbits around it. So all, you know, this light blue and light pinky, you know, are not periodic. So both r equals 1 and r equals 2 periodic orbits are isolated. So they are limit cycles, right? So isolated periodic orbits, okay? So limit cycles. Okay. Yeah. All right. So question, are there periodic orbits that are not isolated? Oh, yes, plenty. So here is an example of a non-isolated periodic orbits. And the example you already know is the harmonic oscillator, okay? So this is how we started the course. And here is the energy function for this one is 1 over 2 x squared. Actually, I can put it. Yeah, okay. Plus 1 over 2 y squared, right? And it's conserved. So along any solution, we have this, okay, this is constant, right? So we can say then that for any solution, we have x squared of t plus y squared of t is constant, and the constant, it's easy, it's really what was at time 0 or the initial time, if it's not 0, the initial time, yeah, okay. So if we do a drawing of this, right, what we would have a bunch of, yeah, okay, something like this, yeah. So here is a picture of the phase space. This is x, this is y, right? And we have this, you know, for every level of energy, we have a different circle if you want, right? And they're concentric. So, you know, because the energy, right, this constant, if you want, this C varies continuously, continuously. okay? You know, basically the POs, these periodic orbits, are not isolated, right? Okay, so I can say varies, you know, C is the energy, right? Total energy. Right? So it could have energy 1, 1.1, 1.2, right? So it's a continuous parameter, right? It's not like it's, I can have only quantas. Like in quantum mechanics, the energy, right, is on certain levels. You don't have in between, right? And that's a different subject. Okay, all righty. So this being said, okay, I can sketch in the last minutes the Hopf bifurcation in itself. But you know something, I'm going to stop now. Okay, so I'm going to do it next time. I'm going to let you be. So, you know, next time I'll have a reason to review this periodic orbits business. And then we're going to do the Hopf bifurcation thing, which is fun, actually. I think is the most interesting one, right? So more complex they become these bifurcations, more interesting they are. So what I can show you already is the picture of the Hopf bifurcation, which I think it's a lot of, it's really nice actually. Yes. Okay. So this is in 3D. We'll have to do it in 3D. Okay. Okay. And it's on one side, we have this kind. Okay, so it's going this way. And here in the middle, we have only periodic ones, non-isolated. Okay, and then this side, okay, I should do the vertical here. So on this side, oops. It's, so these guys are going in, yeah? Whereas on this side, they will go out. They will go that way. So you can see, you know, it's 0. So this is the bifurcation, right? So this would be the epsilon. This is X and this is Y. So it's a 3D picture, okay? So it's on this side, this equilibrium at 0 will be stable, okay? This would, these guys will go in towards that one. Here is neutral because it's just, you know, periodic orbits surrounding it all over, okay? And something like that. And here, you know, is the other way around. They just go away, right? So there is a switch in the middle there at epsilon equals 0. But next time we'll talk about in detail about this. Whereas, you know, for all epsilon, we'll have an equilibrium that survives. It's just that the nature, you know, of the dynamics near this equilibrium changes, which makes it very interesting. Right? I mean, I think it's interesting. Okay. So yeah, that's that. Thank you for your attention. Don't go.